Hello again, and welcome to this next video on Maxwell's equations. In this video, we will look at the second Maxwell equation and also then add in the material equations at the end. So let's get started. This again is all of Maxwell's equations put below each other, and we will now in this video look at this second Maxwell equation called the Maxwell-Faraday equation and where it comes from. So let's first of all put down Faraday's law of induction again. So Faraday's law of induction is given up here, and Faraday's law of induction tells us that if you have a change in the magnetic flux, then we will induce a voltage U. So I brought here this coil, not this coil, this wire loop here, so it's just a single loop, not a coil in that sense. So we have a conductor loop here. And if I put now the conductor loop in space, and this conductor loop has a magnetic field going through it, that means by Faraday's law of induction, if the magnetic field is changing, a voltage Ui will be induced over the open ends of the conductor loop as shown here. So if this is my loop here, and I have the two open ends here, and I would put a voltage measurement equipment to this. If the magnetic field through the loop is changing here, then I would measure an induced voltage at the two open ends here. And how large this induced voltage is, that is calculated by Faraday's law of induction. Okay, now let's go one step further, and we considered here this case that we have the voltage between the two open ends of the loop. Well, what if we put the two ends together? That is, what if we close the conductor? If we close the conductor, as shown here, that still means that the electrons or the charges experience a force in the conductor. So because of that, we will have a current flowing around the conductor here if we have a change in the magnetic field. And if we have a change in the magnetic field, therefore, we have current flow in the conductor. Now the question is, which direction is this current flow going? And that is where Lenz's law will help us, because what Lenz said and found out is that the direction of the induced electric current, so our current that is shown in yellow here, must have a magnetic field that opposes the change in the initial magnetic field. So that is, if we have this current here and we consider the magnetic field of this current, we see that this magnetic field is now going upwards. So this is a right-hand rule again. If you have the current direction like this, magnetic field is like that. So that means we see that if I put in the current direction as done here, it has a magnetic field that is opposing this initial change of the magnetic field. So if this magnetic field here is getting larger, the induced current is getting larger. The induced current then again has a magnetic field that is larger and opposing the original field, and that keeps a balance then at the end. If this current would be pointing the other direction, that is, if we have a magnetic field change that generates a current in the other direction, and then this current in the other direction has a magnetic field going downwards, we would actually get an even larger magnetic field that would give an even larger current, and it would even give a larger magnetic field. So, and in this loop, the magnetic field would self-amplify, and this self-amplification would go on until the conductor is melting away because so many electrons are moving quickly around the conductor. And that is not happening. That would be a perpetuum mobile, so that would be a self-driving system, and that is physically not possible. So because of that, Lenz said, no, that's not the way it's going to go. It's going to work such that the current is flowing in the direction that opposes the original magnetic field change. magnetic field change. So you cannot look just, is the magnetic field here positive or negative, but you have to look at what is the what is the sign of the field change, so the sign of the derivative. That is the important factor. So if the sign of the derivative is positive, we get an electric current as shown here by this direction. So if we have this electric current now flowing around this conductor, it means we also have an electric field, because a current density is associated with an electric field. A current flowing, a current vector is associated with an electric field. So the electric field and the current are related by the conductivity of the conductor. So if you have a certain conductivity, it means we have a certain electric field. And therefore, always if we have current flow in a conductor, we will also have an electric field around the conductor. And that means that this conductor here will carry an electric field that is going in a loop, so that is a closed electric field line, if we have a change in magnetic field going through this conductor loop. And this is what Maxwell actually recognized and added in by extending Faraday's law of induction up here by this front term here. So he said Faraday's law of induction was just calculating voltages. So if we have a gap in the conductor, we can calculate the voltage across the gap. But also if we close the conductor, so if we have a closed loop, there will be a current flowing and there will be an electric field. And that can be described by this this contour integral over the electric field here. So we have to take as the contour, we can take the contour of the conductor, so going once around. It says that if you go once around, the electric field integrated will be the change in the magnetic flux that we had up here in Faraday's law of induction. And this combined equation that is extended by the Faraday effect of the electric field that can loop around is called the Maxwell-Faraday equation. And this is the second Maxwell equation in Maxwell's sets of equations. Let's look a bit more. So far now we were talking about this conductor and how an electric field is excited in the conductor. But actually, this goes a step further because there doesn't need to be any conductor. So if there is no conductor, as shown here, we still get an electric field. So that is magic. So you have a change in the magnetic field and you get an electric field in free space. You don't get, if it's a vacuum and you don't have any charges that can move, you don't get any current that is flowing. But you still will get an electric field that is forming a loop around the change of magnetic field. So you get these looped electric fields going around changes of the magnetic field. And this electric field is actually observed in vacuum, and this is what is called an electromagnetic wave. And the first electromagnetic waves were experimentally shown by Heinrich Hertz. And Heinrich Hertz actually did the theory for these experiments here at Kiel University already quite a while back. But actually in the building where I'm standing here, one of the lecture halls downstairs is called the Heinrich Hertz lecture hall, because Heinrich Hertz exactly predicted that, well, if this is all linked in vacuum, we don't need any medium to transport electric and magnetic fields. But if you have a change in magnetic field, we get a change in electric field. A change in electric field will again cause a change in magnetic field due to the first Maxwell equation. And then this change in magnetic field will again do an electric field, change in magnetic field, change in electric field, and we will get a propagation of an electromagnetic wave in space. And this is also now included, and it's also coming from Faraday's law of induction originally, but Maxwell extended it to this case of the electric field also being generated without any conductors there. So therefore, if we now put the equations together, we have this first Maxwell equation, that is Ampere-Maxwell law, that is based on Ampere's circuital law. we have the second Maxwell equation, that is the Maxwell-Faraday equation, that is based on Faraday's law of induction. The other two Maxwell equations, 3 and 4, relate the sources of the respective fields. So this here is also called Gauss' law, the third Maxwell equation, and it states that charges are the source of the electric field. And this integral here, so this closed surface integral, means that you take the integral enclosing a complete volume, so you integrate over the surface enclosing a complete volume, and if you have Q charges in the volume, the result is that you will have electric field lines coming out of the volume or going into the volume. On the other hand, the magnetic field is source-free. That means, if for the equation 4 here, if you integrate the magnetic field over a complete surface enclosing a volume, then you will find that the same magnetic field is going into the volume as is coming out of the volume. And that means there are no monopole sources of magnetic field. Magnetic field is source-free for the calculation. And these are the 4 Maxwell's equations that Maxwell summarized the experimental findings in. Now, as I already announced, we have to look at the material equations as well in order to link the different properties. And the material equations are given down here. So this is the material equation that links the electric displacement to the electric field by the vacuum permittivity multiplied with the relative permittivity of the medium. Then the second material equation here links the electric current density vector to the electric field by the conductivity kappa. The third equation links the magnetic flux density vector to the magnetic field vector by the vacuum permeability mu naught multiplied with the relative permeability of the medium mu r. These material equations, as they are given here, are true for isotropic media if they are just scalar properties. Particularly in magnetic materials, we often have anisotropic properties. That is, in a magnetic, for example, an iron material, a ferromagnetic material, we often have a permeability that depends on the orientation of the medium. In order to describe that, we have to extend these material equations here. And this extension we do by considering material tensors. So for the isotropic case, we have here these kind of simpler equations with the scalar material properties. As soon as we have an anisotropic material, we have to look at the material tensors. These material tensors are put down as matrices, so you can see them, they look like a matrix here. And how this works is then, so the magnetic field has 3 components, the x, y, z component of the magnetic field, also called 1, 2, 3 components often. And these magnetic field components must be multiplied then with this row. For the first component has to be multiplied with this first row in order to obtain the first component or the x component of the b vector. So the x component of the b vector is given by mu r11 times the x component of the h vector plus mu r12 times the y component of the h vector plus mu r13 times the z component of the h vector. And therefore, as we have this sum of 3 different components that point in x, y, and z direction, the b vector does not necessarily have to have the same direction as the h vector. That is actually only true if we are in the isotropic case here. As soon as we have elements that are not isotropic, as we have elements here in this tensor, so mu r12 and mu r13, we will observe that the h vector and the b vector are not pointing in the same direction anymore. I should not say just in the isotropic case, because you can think if it's only a diagonal here, so if you only have diagonal elements, they can actually have different amplitude, but still H and B will both point in the same direction. It's just that the proportionality factor is different for the different spatial components. So if you're considering materials that are not isotropic, that is, that don't have the same material properties in all three space directions, we typically write this down in this way of giving the tensors, and the tensors include all the different material properties for the different directions. Thanks for watching. See you next video.